Hey Aaron, how's it going? It's good. Hey guys.
Good. The homework was surprisingly good.
Okay, that's good.
I do have, I just started today.
Okay.
I got 2B and 2C done.
Okay, that's great.
But,
That's great.
2B is a bit confusing in terms of how to compute. I haven't even tried it.
Okay.
I'm just talking about.
I set it up, I actually want to talk to you about after.
Okay.
I'm talking about in terms of how to set up the stiffness matrices when you have to combine a truss and a spring.
Oh, for sure, for
You
sure.
literally just combine them where the nodes are overlapping.
Yeah, when they overlap, you just add them together.
Yeah.
Yep.
No, but I mean, like, you have a spring on two, like, you have the two attached to each other, right?
Yep.
So what do? F1, F2 is equal to K1, and then you have the big multiplier on the part where the truss is?
Yep.
Okay.
Yeah, you just add them together. Yeah, that's why I showed you, when you have things overlap, I draw like the outline of where the stiffness is, and just wherever they overlap, whatever's there from either stiffness matrix, you just add them together.
So like, for example.
Oh, I thought that was in the global system you showed us that.
Yeah, yeah, and in the global system, that's the only place where you combine them. So
Yeah, so do you remember 2B? Like,
Yeah, yeah.
Vaguely?
yeah, yeah.
So
Mhm.
like, for the first part, right, you would just set up the spring stiffness matrix, right?
Yep.
And
Mhm.
at node 2, you have a spring connected to a truss, so you have, so you use just the truss equations, right, in that one?
Yep.
And then so on, you just keep going down the line, and then you
Oh.
combine with the global.
So you just
Where you
add
at
that
the
together.
node 2, you'd have a stiffness matrix for a spring and a stiffness matrix for a truss.
Yep. Just
Okay,
add
that's
them.
not nearly as hard as I thought.
Yeah.
Oh, but Dr. Tran, so, but then like, so on number, I had a question too about number 3.
Mhm.
Did you define this way as positive? Because you have P going this
Oh yeah,
way.
yeah, yeah. Someone asked me that. I think I just missed the negatives in my solution. So they should all the magnitudes are right, but I just missed the negatives. So.
Okay, yeah, and then on this one, when I put it positive, I got the reverse sign, and then I was like, okay, he must have defined it negative, so then I put it negative.
Yeah. My signs are I'm not as disciplined as I should be.
Okay, I was just wondering about that.
Mhm.
If we use MATLAB, do you want the spreadsheet?
Yeah. If you just show me the system that you made. All right, it's 7 o'clock, so let's go and get started. All right, good evening, everyone. How's everyone doing today? Good. Happy Valentine's Day. Everyone's doing the fun thing on Valentine's and spending it in class, and so you know we're all together on that front. Super Bowl was yesterday too. So I feel honestly, I'll be honest with you, I feel awful right now because yesterday, me and my friends we met up for the Super Bowl, but we had the brilliant idea of, well, no one had the brilliant idea of bringing any food, and so the only thing we ate for basically lunch and dinner yesterday was just snacks, and so there was like a 24-hour period where like the only thing I had eaten for that 24 hours was just chips and gummy worms, and so I felt awful after that. And then this morning I woke up and then I had to take care of something, so I didn't get to eat breakfast. And so lunch today was the first time I had anything of substance. And so yeah, I feel awful right now. So if I'm a little bit out of it today, then I apologize. No tequila. And so we literally everyone just brought snacks, and so we didn't really organize it. So we said everyone just kind of bring food, and so no one brought drinks and everyone brought snacks, and so that was kind of bad planning on our part, but you know, now we suffer the consequences. Yeah. Okay. And so with that said, let's so the plan for today is mostly we're doing examples today. And so I think last time we talked about how to do 2D truss problems. And so today we're actually going to do some examples to see, you know, how you actually do this. So I know quite a few of you have already started the homeworks. And actually, a lot of you have actually already started doing the 2D problems, which you know I'm very happy with, and so you know great job for those of you who have done it. And so for those of you who are at that point, or maybe you haven't started yet, hopefully today's lecture will help you get will help you see a few different cases where you can you know how to actually apply this stuff. Okay, because these problems, you know, they aren't you know tricky in a sense. But they are very long, and so they involve a lot of calculations, and you know it can be quite a slog to kind of get through everything. And so, you know, but besides that, you know, it's a very systematic process. It's just you know trying to stay disciplined and try to stay you know awake during these problems. I think that's going to be the hard part. All right, and so with that, are there any questions I can answer before we get started? Okay. All right, so let's go ahead and jump right into it. And so we were, last week we were discussing 2D truss and spring problems. All right, and so let's go ahead and jump right into an example. And so for this example here, what I have is a three element assembly. Two of these elements are going to be trusses, and one is going to be a spring, actually. Okay. And so we're going to have an element like this. Okay, so we'll call this element A. Give a horizontal element like this. We'll call this element B. Okay. In addition to that, we're going to have a spring, which is going to go up like that. Oh, excuse me. The spring is B, and the bottom truss is C. So this is B. This is C. Okay. So this is pinned to the wall. This one is pinned to the wall. This one's also pinned to the wall. Okay. This angle right here is 45 degrees. This angle here is 45 degrees. Okay. This is node 1. This is node 2. This is node 3. This is node 4. Right, and we're going to be pulling down with a force of 10,000 pounds. Okay. All right. And so let's list out the properties of these elements. And so let's start with the trusses. And so for elements A and C, okay. For elements A and C, they're going to be identical. And so they're going to have a Young's modulus of 30 times 10 to the 6 psi. Okay. The area, what we're going to say is 2 inch square. Okay. and their length are going to be 10 feet. Okay. And for spring element B, we just have one property here, which is the spring constant. And so the spring constant of element B is going to be 250,000 pound per inch. Okay. All right. And so we're under this setting here, what we want to do is we want to use the direct stiffness method to compute displacement at node 1. Okay. As well as the stresses in elements A and C. And so in our two truss bars, once we have our displacement solution, we can use that to compute the stresses using the formulas and techniques that we went over at the very end of class on Wednesday. Okay, so here's the problem setup. So there's these finite element problems. There's always quite a bit to write down because we have to write down every single element, the properties for every single element, and how they connect and all that stuff. Okay. And so, first thing to do, with these problems that, half the mistakes that I see often is, just make sure you write down everything correctly about the problem. All the angles are there, all the properties are there for the right elements, and, make sure everything matches up with what it should be. All right. Any questions about the problem setup? Okay. All right. So let's go ahead and start solving this. But, even though we're in 2D, we still follow the same recipe or same algorithm that we did before. Okay. And so we're going to start with the element stiffness matrices for each element. Okay. All right. So this is always your first step for these direct stiffness problems, is to take each element in your problem and then write out its element stiffness matrix. Okay. All right, so for this one, we have three elements. And so let's start with element A. Okay. And so let's go ahead and write down. So for these 2D problems, it's useful to write down the angles for each of these elements. Okay. And so for this element, it's pointing vertically upwards, right? So we have node 1 down here, node 2 up here. And it's pointing vertically upwards. And so the angle that it makes with respect to the horizontal is 90 degrees. So if theta here is equal to 90. Okay. And so if we compute the trigonometry terms, so we have cosine of 90. So cosine of 90 is, of course, 0. Okay. And sine of 90 is 1, right? And so the element stiffness matrix is going to be which, remember, we're in 2D now, and so it's going to be a 4x4 system. Okay. And so if we look at the nodes that it's connected to, it's connected to nodes 1 and 2. And so we're going to have F1x, F1y, F2x, F2y. Okay. This is equal to AE divided by L for this element. Okay. Multiplied by, and I'm going to go ahead and mark the columns. So U1x, U1y, U2x, U2y. Okay. And it's going to be multiplied by U1x, U1y, U2x, U2y. Okay. All right. And so from here, we're going to go ahead and write in our element stiffness matrix. Okay. So I'm gonna write down kind of the general form here just once, and then I'm just gonna kind of fill in the values after that. Okay. And so based on the transformation matrices that we talked about last Wednesday, then the entries in this matrix are, in the top right, we have cosine squared, then we have cosine times sine, then we have minus cosine squared, then we have a minus cosine sine, okay? Then we have a sine squared, minus cosine sine, minus sine squared, okay? Then we have cosine squared, cosine sine, and then down here we have sine squared, okay? And of course, like we talked about before, once you have the top side of this matrix, you can just make it symmetric. And so you can go ahead and write the entries on the bottom side, okay? All right, so for this particular matrix here, so let me go ahead and write down, everything again. We can go ahead and plug in for AE over L. And so if we multiply this, and so we have 30 times 10 to the minus 6, or 10 to the 6, we have 30 E6 multiplied by area. So area here is 2, okay? We're going to divide by the length. And so the length here is 10 feet. And so we need to convert this to inches just to make sure that everything matches up unit-wise. And so this is going to be 120 inches, okay? And so we plug all those things together, and what we get is, let me go ahead and turn the page again, 5 times 10 to the 5th. Okay, and this is pound per inch. Okay. All right, so if we go ahead and write this in, 5, I'm going to write it down right here. Yeah. So this is 5 times 10 to the 5th pound per inch. Okay. So that's AE over L for this element. Okay. And we can go ahead and fill in this, this matrix now, right? Knowing that cosine is 0 and sine is 1, right? So first we have cosine squared. So we have 0 times 0, which is just 0, okay? Then we have cosine times sine. And so cosine is 0 and sine is 1. So we have 0 times 1, which is still 0, okay? Then we have minus cosine squared. And so this is, again, going to be 0, okay? And then we have a minus cosine sine where this is 0. Okay. Right, so the entire first row here is 0 in the case where you have a theta is equal to 90 degrees. All right, so let's go to the second row. Second row, we have a sine squared. And so sine squared here is going to be 1, right? Because we have 1 times 1. Then we have minus cosine times sine. We have minus 0 times 1, which is 0. Okay. And then we have a minus sine squared, which is minus 1. Then we have cosine squared. So cosine squared is going to be 0. Cosine sine is going to be 0 as well. Okay. And then finally, in the bottom right of the matrix, we have sine squared, which is going to be 1. All right. And so now that we have the top half of the matrix done, we can just go ahead and take the rows and write them into the columns because this matrix is symmetric, right? So let's take this first row and write it into the first column. So we have 0, 0, 0, right? So all I did was I took these entries here and kind of wrote it down in there, okay? So that's kind of one easy way to write a symmetric matrix. Next, we have the second row, and so we have a 0 here and a minus 1 here, okay? And then finally, for that last entry, we have a 0. Okay. Right, and so this right here, this is our element stiffness matrix for element A. Right? Any questions on how we got this? Okay. All right, so next let's do element B. All right, so element B here is our spring. And so the only property for the spring is going to be the spring constant, which is 225,000 or 250,000. Okay. And so if we write this in a scientific notation, 250,000 is the same thing as 2.5 times 10 to the 5th pound per inch. Okay. The theta for this element, you can see here that our element B here is rotated up by 45 degrees, right? And so if the node 1 is down here, the node 3 is up here, and we draw a line just like that, we can see in order to get to that point, we had to rotate counterclockwise 45 degrees. Okay, so we have theta here is equal to 45 degrees. Right. Cosine of 45 is, of course, root 2 over 2. Sine is root 2 over 2. Okay. And we can go ahead and start filling in the matrix using the exact same formulas that we have up there. Okay. All right, so for node for node 2, or excuse me, for element B, it's connected to nodes 1 and 3. So we have F1x, F1y, F3x, F3y, okay, is equal to, oops, you have to have the spring constant on front. And so the spring constant is 2.5 times 10 to the 5th pound per inch. Okay. Right, and so we have U1x, U1y, U3x, U3y, and then U1x, U1y, U3x, U3y. Okay, so let's start writing these in. And so first we have cosine squared. So we have root 2 over 2 times root 2 over 2. And so that's going to be 1/2. Okay. Next we have cosine times sine, which is a root 2 over 2 times root 2 over 2. So again, we have 1/2. Okay. Our next entry is a minus cosine squared, and so that's going to be a minus 1/2. And then finally we have a minus cosine sine, and so that's going to be another minus 1/2. All right, and so that's the first row. Second row, we're starting off with a sine squared, and so sine squared is going to be root 2 over 2 squared, and so that's again going to be 1/2. Okay. Then we have a minus cosine sine, and so that's going to be a minus 1/2. We have a minus sine squared, which is going to be a minus 1/2. Okay. Then we have the third row. So third row starts with cosine squared, and so that's going to be a positive 1/2. Then we have cosine sine, and so that's going to be a positive 1/2. Okay. And then finally, in the bottom right, we have a sine squared, which is going to be another 1/2 there. Okay. All right, so just like I did above there, I'm going to take the first row and write that into the first column. And so that's going to be a 1/2, minus 1/2, minus 1/2. Okay. Next row, we're going to have a minus 1/2, minus 1/2. And in the last row, we have just a 1/2 there. Okay. And so this entry, and so this matrix right here, this is our element stiffness matrix for element. All right. Any questions on this? Okay. Okay. So now let's look at element C. Okay. And so element C here, we have the same EA over L as element A, and so this is going to be 5 times 10 to the 5th pound per inch. Okay. But for element C right here, our theta here is 0, right? Because we have just a horizontal element. Okay. And so if we kind of draw an arrow like that, you can see that element C here aligns with the x-axis. Bless you. And so the theta for this is going to be 0 degrees. And so cosine of 0 is going to be 1, and sine of 0 is going to be 0. Okay. All right, so let's go ahead and write in the element stiffness matrix for this one. Let's look at the nodes that it borders. And so element C here is going to be connected to nodes 1 and nodes 4. Okay. And so we have F1x, F1y, F4x, F4y. Then out in front, we have a 5 times 10 to the 5th pound per inch. Okay. Right. And so if we write in the components, we have U1x, U1y, U4x, U4y. We have U1x, U1y, U4x, U4y. Okay. All right, so we're going to start off with a cosine squared. So cosine squared is 1 squared, which is 1. Okay, then we have cosine times sine, which is 0. Then we have a minus cosine squared, which is -1. And then we have a minus cosine sine, which is 0. Okay, so that's the first row. Second row, we start off with a sine squared, and so sine squared is going to be 0. Okay. Next, we have a minus cosine sine, and so that's still going to be 0. And then we have a minus sine squared, which is still going to be 0. Okay, so the third row, second row is all zeros. Next row, we're starting off with a cosine squared, and so that's going to be a +1. Then we have a cosine times sine, which is going to be 0. Okay. And then finally, in the bottom right, we have sine squared, which is going to be 0. It's just 0 squared. Okay. All right, so same thing I did before. Let's take the rows and write them into the columns. And so we have 1, 0, -1, 0, 0, and then 0, just like that. Okay. All right, and so that's the element stiffness matrix for element C. Okay. Right. And so, if you have elements whose angles are either 0 degrees or 90 degrees, something of the the cardinal directions, it saves you a lot of time because when you have either one of the sine or cosine terms equal to 0, that saves you a lot of work because that's going to cancel out a bunch of the terms in our matrix. Okay. Any questions on this? Okay. All right. So now that we've written all the element stiffness matrices, the next step is assembly. Okay. Remember, assembly is we take each of the element stiffness matrices and we put them into a gigantic, linear system, the global linear system. Okay. And so this is going to be really hard. This is the part that I hate the most of writing on iPad because it's such a small thing, but I'll try my best. Okay. All right, and so since we have 4 nodes in our 4 nodes in our domain, then we're going to have 8 degrees of freedom, right? And so we're going to have 8 equations and 8 unknowns. And so our global stiffness matrix here is going to be 8 by 8. Okay. So U1x, U1y, U2x, U2y, U3x, U3y, U4x, U4y. Okay. All right. 8 by 8, right? I know it takes up a lot of space, and so I think my solutions for this homework was about 10 pages long, and so a lot of that is just writing these gigantic matrix systems. And so, I know it takes a lot of space, but that's just the nature of these kinds of problems. Okay, and so before we actually start filling in values, what I like to do, especially when you're first starting out, is to do our box method, and sort of box out basically the regions of the global stiffness matrix where we're going to insert our entries of the element stiffness matrices. Okay. All right, so let's start with element A. Okay. So element A was bordering nodes 1 and 2. Okay. And so nodes 1 and 2 are going to be these 4 columns right here, and the first 4 rows of the matrix. Okay, so that's element A, and so that's a block reserved for element A. Next, we have element B. Okay. So element B is connected to nodes 1 and 3. Okay. And so this is not a continuous entry. And so we're going to have to break up this element stiffness matrix. Okay. And so first thing we have is a 2x2 system up here for the first 2 rows and the first 2 columns. Okay. Then we have an entry down here for these 2 rows and these 2 columns. Okay. Then we have one up here. Okay. And then one in the 3-3 slot, which is down here. So remember, be careful about these, systems where you have to break it up because, a lot of times it might not be obvious. But for 2x2 systems like this, the X and Y components of each of the nodes are clustered together. And so make sure you keep those together. And so for 2D problems, you're going to break up your element stiffness matrices, but make sure you keep, those 2x2 clusters together just like that. All right. And so finally, we have element C. Okay, so element C is nodes 1 and 4. Okay, and so for nodes 1 and 4, we have this box right here, and so a lot of action on this one node. Okay, which makes sense because they, all 3 elements are connected at node 1, and so whenever you have multiple elements connecting at a single node, those areas are going to be pretty busy in the global stiffness matrix. Okay. Then we have another box right here, box right here, okay. And then finally another box just like that. Okay. In the 4-4 slot. Okay. And then everything else is zeros. And so anything that's not boxed, you can just go ahead and fill in zeros for them. Okay. Okay. And so next thing I'm going to do is I'm going to fill in this all the colored entries with the appropriate values. Okay. Before I do that, are there any questions of why I box these areas and my logic behind all this? Okay. All right, so let's go ahead and start filling in. And so let's start with element A. So element A is pretty simple. And so we have 0, 0, 0, 1. But the 1 is multiplied by 10 to the 5th. And actually, let me do this just to make things simpler. And so I'm going to pull out a 10 to the 5th out here, just so we don't have to worry about it. And so this is going to be 5. Okay. Then we have 0, 0, 0, minus 5. Okay. And then we have another row of zeros. And then we have 0, minus 5 here, and 0, 5. Okay. All right, so that's element A. Relatively easy. Okay. Next, we have element B. And so element B is the one with a bunch of 1/2s. And so this is going to take a little bit of time. Okay. And so for element B, let me do this actually. So let me go ahead and zoom into this area right here. Okay. And so element B is going to be added to this part right here. And so we're going to add a 1/2 multiplied by 2.5 times 10 to the 5th. And so 1/2 of that is going to be 1.25. Okay. We're going to plus 1.25 plus 1.25 plus 1.25. Okay. Right. Right. And so those 1.25s come from the fact that we have a 1/2 inside the matrix here, and we're multiplying by the coefficient in front, which is 2.5 times 10 to the 5th. Okay. And then we're going to fill in all the other parts. And so we have a minus 1.25 here, minus 1.25, minus 1.25, minus 1.25. We have minus here, minus 1.25, minus 1.25, minus 1.25, minus 1.25. Okay. And we have a positive 1.25, 1.25, 1.25, 1.25. Okay. And then finally, we have the element C. So element C is nodes 1 and 4, but it's really easy. And so we have mostly zeros except for ones in those entries. Okay. And so element C, the coefficient out in front is 5 times 10 to the 5th. And so we're going to add that here. And so it's going to be plus 5, okay, plus 0, plus 0, plus 0. Okay. Next, we have a minus 1, 0, 0, 0, 0. And so we have a minus 5, 0, 0, 0. And we have a minus 5, 0, 0, 0. And then a 5, 0, 0, 0. Okay. All right. And so we can go ahead and simplify this because the top left here is kind of a mess. And so if we go ahead and substitute the proper values here, you write this in purple because we had a lot of overlap here. And so we write this in. This is going to be 6.25. This one's going to be 1.25, 1.25, and then 6.25. Okay. Because remember, whenever you have element stiffness matrices that overlap in the global stiffness matrix, all you simply do is just add their values together. All right. And so that's assembly for this problem. So are there any questions on this? Okay. Yeah, for sure. Yeah. So remember, these problems, they're very long. They take a while, and so it's already been 30 minutes, and we just finished assembly, and so these problems I think are not. They're not world breaking, but they are patience breaking. I think that's what I like to think about them. Yeah. But also hand breaking. So depending on how efficient you are, then it takes a lot of writing. It can hurt your hand, especially when you're writing a bunch of zeros and stuff like that. Yeah. All right. And the bad thing about these problems is because of the boundary conditions, you end up, erasing a lot of this work because you're going to be replacing a lot of these rows. Okay. All right, and so the next step after assembly is to apply our boundary conditions. Okay, and so our boundary conditions for this are that we have a ton of fixed supports. Okay. Okay, and so we have fixed supports on nodes 2, 3, and 4. A question. So will it be time consuming to do on the exam with this problem in person? Yeah, so that's the challenge I'm dealing with with writing the exams. And so it's hard to get away with how time consuming these problems are. But the way I've done it in the past, and I gave an undergraduate version of this content last semester. And what I promised all the students in that class was that the problems that we do in the exam in person, I'm not going to give you more than 3 elements, because anything more than that, it just kind of becomes ridiculous. And so no more than 3 elements and no more than 4 nodes. And so that's what you can kind of expect. And so what the undergraduates told me last semester was that they kind of just got a lot of these, just kind of almost became muscle memory, and then they just kind of wrote them down really quickly. And it worked out well. I think the average for my undergraduates for that exam was about 80%. Yeah. And the problems were very similar. They're not that much more complicated than what we're doing on this example. So this example was kind of the level that you would kind of expect on the exam. Okay. And so with nodes 2, 3, and 4 fixed, and so that tells you that all of their displacement components are 0. I mean, it's taking us longer to do it here just because, you know, we're talking through every step. But if you knew every step and you just kind of wrote it through, then that takes, you know, that saves you some time too. Okay. And so with nodes 2, 3, and 4 fixed, that means all those components are going to be 0. Okay. And so we can go ahead and write those into the matrix, right? Okay. And so on the forcing vector on the other side equation, and so we have 0, 0, 0, 0, 0, 0. Okay. Because remember, when we apply our Dirichlet boundary conditions, we replace the entire row of the matrix with those with the appropriate values. Okay. And so we replace, you know, the entire row with zeros. For this row's case, it's almost all zeros already. Okay. That should be this one. And then we put 1 on the diagonal. Okay. For the second row, the only entries that we have here are, you know, this -5 and this 5 right here. Okay. And so we're going to put a 0 here and a 1 here. Okay. To represent that equation. For this next row, we have quite a bit to erase. Okay. Okay. And so that's how the F3X row looks like. Now we have the F3Y row. Okay. And so we're going to erase everything that's not a 0. And then we're going to put 0, 0, 0, 1. Okay. Right. And then finally for the F4X row, we have a 1 there and a 1 there. Okay. All the ones on the diagonal. Okay. And then finally, you know, for the, you know, now that we have the, all the Dirichlet boundary conditions taken care of, now we have the Neumann boundary conditions, which is the modes. Okay. And so we've applied a load applied on node 1, and it's in the negative y direction. And it has a value of what? It has a value of 10,000 pounds. Okay. And so remember, the way that we apply Neumann conditions is that we just simply plop the load values into the right-hand side vector. Well, in this case, it's the left-hand side vector, but you know, the forcing vector. Okay. And so we have no load in the x direction on node 1, but we do have a minus 10,000 on node 2. Okay. All right. And so that's it. And so, you know, we've constructed our global linear system. We've applied the boundary conditions, and now we're ready to solve. Okay. Any questions on this? All right, and so now that we've reached this point, our linear system is ready to solve. And so we can go ahead and take this linear system. You can plug it into MATLAB, or if you prefer a graphing calculator, then that's fine too. Okay. Just don't solve it by hand. So that's pretty rough. Yeah.
So the order of making an element matrices and assembling it, and then you apply the boundary condition, that has to be followed. It can't just zero out the boundary condition.
So, you know, because these problems are so time consuming, if you already know that a particular row is going to be zeroed out because of a support, then you can go ahead and do that. And so for right now, I'm showing you kind of the full process, but you know, like, especially when you start doing these problems and you get tired of writing all these down, like you look at a geometry like this and you know right away, like node 2 is going to be zeroed out, node 3 is going to be zeroed out, node 4 is going to be zeroed out. And so you can go ahead and skip to those, just kind of go ahead and write that into the matrix just to save yourself some time. And that's totally fine. Yeah. So the only thing I would be careful of is that make sure that you don't forget to add certain entries. And so what can happen, what I've seen happen, and what I've done myself too, is I say, okay, you know, element B here, node 3 is going to be crossed out. but then I forget to add, you know, these two rows or something like that because that's so. You know, you can definitely cross things out beforehand just to save yourself some time, but you know, just make sure that you're doing everything there. Yeah. All right, and so if we solve this in MATLAB, what we get is u1x is equal to a 0.0033 inches. Okay. u1y is going to be equal to minus 0.0167 inches. Okay, and everything else is going to be 0 because they're fixed to the wall. Let's make sure we don't forget our units. Okay, and there's your solution. All right, question. So can you incorporate this problem into Ansys? Yeah, absolutely you can. And so what you can do is you can basically incorporate each of these slender objects as a beam element. Okay. Because you can because in Ansys Ansys gives you the ability to define these slender type elements. So very similar to what we're doing here. And then you can apply the loads exactly the same way, make sure the material property is the same. And you should get similar solutions. Maybe not exactly because I think in Ansys they don't assume, because right now we're making the assumption that our displacements are only, you know, tensile and compressive. But I think in Ansys, I think you might have to do some special settings in order to set that. But you know, you should get pretty close in Ansys to what we get here. Okay. All right. And so now that we have the solution, we can go ahead and use this. Okay. And so, you know, to use this solution, I'm going to go ahead and use this to compute our stresses, right? Because remember, that was the last part of the problem. Okay. And so we're going to compute stresses in elements A and C. Okay. All right, and so if you recall from the end of class on Wednesday, the way that we compute stresses is we take, you know, the Young's modulus of the element, we divide it by the length of the element, okay? Then we multiply by the vector minus cosine of the element, minus sine, times cosine times sine, okay? And then we multiply this vector right here by the vectors of by the vector of displacements, okay? And so we just simply perform, it's basically a dot product between this cosine, the sine vector, and the displacements of that element. Okay. All right, so what do I mean by that element? And so it has to be the displacements that that element is connected to, okay? Remember, each element is always connected to two nodes. And so this UIX, UIY, UJX, UJY, they have to be the nodal displacements of that particular element. Okay? All right, so let's start with element A first. So element A, remember the theta here for that element is 90 degrees, okay? And element A is connected to nodes 1 and 2. Okay. And so the stress in element A is equal to the Young's modulus divided by the length, multiplied by cosine of the angle, which is just 0. Then we have minus sine, which is minus 1. Then we have 0 for cosine and 1 for sine. Okay. And we're going to multiply this by the displacements of the nodes that it's connected to. So it's going to be u1x, u1y, u2x, u2y. Okay. And we go ahead and plug in the solutions that we have above. And so u1x is 0.0033 inches. Okay. U1y is minus 0.0167 inches. And then U2x, U2y is equal to 0, okay? And so we perform this multiplication, knowing that we know the Young's modulus and we know the length, and we get a stress of 4,075 psi. So element A is under a stress of 4,175 psi. Okay, and the fact that we got a positive number here tells us that this element is in tension. Okay, and so element A is being stretched. It's being stretched out. It's being stretched out with a tensile stress of 4,175 psi. Okay, and so now let's do element C. Okay, so element C again is going to be E over L times the angles. Okay, where theta C here was 0 degrees. Okay, and so we have a minus cosine, so we have a -1, minus sine, which is 0, cosine is 1, sine is 0. Okay, and element C here is connected to nodes 1 and 4. So we have U1x, U1y, U4x, U4y. So we have 0.0033 inches, okay, minus 0.0167 inches, and 0. Okay. And so we have sigma C is equal to minus 825 psi. Okay. And the fact that we got a negative stress here tells us that this element is in compression. And so once you find the displacement solution for these elements, you just have to plug it into this formula here, and then it'll give you the stresses in that element. Okay, but you can only do this for truss elements, and so you can't do this for springs. And so springs, springs experience stress too, but it's because the spring is a coiled structure, it's not a straight thing. The way you compute stress is a little bit more complicated in springs, and so we're only going to worry about truss elements here. Okay, any questions on the stress calculations here? Okay. All right, so that was a long example. It basically took us 45 minutes, but we ran through everything. And so that example kind of had everything that you need to know about these problems. And so, and so for those of you who are already attempting the 2D problems on the homework, you probably already understand that these problems can take a while. Especially the first time that you're doing these problems, because it's a lot of calculations and there's a lot of little areas where things can go wrong. So make sure you kind of take these slowly, and especially because it's your first time. Okay, and so for this next example, I did want to introduce a couple new ideas. Okay, and so the first new idea that I want to go over is the idea of a roller support. Okay. And so, so far, in the examples that we've done, we've only really looked at fixed supports or pin supports. Okay, and a fixed support and a pin support is unique in that it eliminates both components of displacement. Okay. Or they knock out both ones. But not all supports are like that. And so you can have a roller support which only knocks out one component of the displacement. Right, so visually, it looks something like this, right? And so you're going to have a triangle here to indicate the support, okay? Normally, when this is fixed, this triangle is fixed into the ground, but for a roller, we put it on basically roller skates, okay? And so those roller skates tell us that, this support here is free to move in this direction, okay? Okay. But it cannot move in the Y direction, okay? And so I think, there's always kind of this question about roller supports because they look like a roller skate basically. And so of course, if you have ground like here, then of course it's going to prevent any motion in the negative direction here, okay? But just from the picture, it looks like it can allow motion in that direction too. And so if this were a pure roller skate, you would be right. But the way I kind of imagine these roller supports is that we have wheels that are inside a track, okay? And so the track allows them to move, along the track, but it doesn't allow them to move perpendicular to the track, okay? Okay. And so for this particular case, let's say that this is node 1 right here, then U1x would still be free, okay? And so it's still able to move in that direction, while U1y, this is constrained. Right, and so if you see roller supports in your problems, make sure that you only knock out just the component of the displacement that's constrained, okay? And you leave the other one alone. Okay, any questions on this? Okay, all right, so let's go ahead and do another example. And we'll work through this one much faster than the last one, okay? So this one's only a two-bar assembly. What's going to be different about this one is that it's going to have a roller. Okay. All right, so let's go ahead and do this. Okay. And so this top constraint here is going to be a pin. Okay. So we have one element that comes down like this. Another element that comes over here like that. Okay. And we'll say that this one's a roller. Okay. So it's going to be inside a track. And so this one here is going to be node 1. This is going to be node 2, node 3. Okay. This is element A, element B. Okay. Let's assume the length of element A is 10 feet. And the length of element B is 5 feet. Okay. So of course, this drawing is not drawn to scale. Okay. Oops. All right. And then the angle between these, we're going to say is 30 degrees. Okay. Okay. And so besides the length, they have the same, both truss elements here have the same properties. And so the Young's modulus is going to be 30 times 10 to the 6 psi. Okay. And the area is going to be 1 inch squared. Okay. Okay. And so for this problem, let's compute displacements at all the nodes. Okay. All right, so the geometry a little bit simpler in this case. We only have 2 elements to deal with 3 nodes, and so we should be able to knock this one out faster. But there are a couple wrinkles in this one that we haven't seen before that I want to make sure that we cover. But before we get into solving this problem, are there any questions on the setup? Okay, all right, so let's go ahead and start solving it. And so let's start with the element stiffness matrices like we always do. Okay. All right, so let's start with element A. Okay. First thing we're going to do is we're going to compute EA over L. Okay, so EA over L in this case, we have a 30 times 10 to the 6 psi times A, which is 1, and then we're going to divide that by the length, which is 120 inches, and so this gives us 2.5 times 10 to the 5th pound per inch. Okay, and so that's going to be the coefficients that we put out in front of our element stiffness matrix. Okay. Okay, now we get to the angle. And so this is where the wrinkle kind of shows up. Okay. And so it's tempting in this problem, because I give you the angle there is 30 degrees, to say that the angle for this problem is 30 degrees. Okay. But of course, because I'm telling it to you like that, then it's not going to be 30 degrees. Okay. But it's going to be related to. And so the angle for this one, believe it or not, is 150 degrees. Okay. And so how did I get 150? And so let's look at the geometry for element A. The geometry for element A looks something like this. So this is node 1, this is node 2, right? And we know that this angle right here, this angle right here is 30 degrees. Okay. And so how did I get 150 from this? Well, let's do this. And so, when you're deciding what angle to assign for your elements, what you should do is you should go to the lower number element and draw in your coordinate axes. Okay. Okay. And so in this case, the lower number element is node number 1. And so I'm going to go ahead and draw my coordinate axes on that one. Okay. And then what I'm going to do is that I'm going to draw a vector arrow from the lower number element to the higher number element. Okay. And so in this case, it's going to be an arrow that looks like that. Okay, so this arrow right here. So the vector from lower node to higher node. Okay. Right. And then the angle that you have is going to be the amount that you rotate counterclockwise from the positive x-axis to reach that vector. Okay. And so in this case, we're going to start from the positive x-axis, and you can see to get there, we rotate this much, okay? Right. And so that amount of rotation there is going to be 150 degrees, okay? Because that we know that if we make a full half rotation, then we're going to end up at 180, but we don't end up at 180. In this case, we have the 30 degrees on the bottom right here. And so the angle is going to be, one way you can interpret it is 180 minus 30, which is 150. Okay. All right. And so with our angle at 150 degrees, then our cosine of that angle is going to be minus √3/2. Okay. And our sine of the angle is going to be 1/2. Okay. Any questions on how I obtained that? Yeah. Yeah. Exactly. Yeah. Yeah. So if the one was up top, then you would rotate all the way around it. So that would be 330 degrees. Yeah. So the reason I have this convention is just to kind of make it consistent. And so messing up, and so misplacing the angles is a common way for these problems to go awry. Because if you aren't consistent with how you define the angles, you're gonna run into situations where you compute the finite element result, and I didn't apply a force here, and so the force here is going to be downwards of 25,000 pounds. Okay, and so if you reverse the angle, and so if you assign 30 degrees instead, what you might obtain from your finite element result is that u1y might be a positive 1 inch or something like that, right? And so the solution is going to tell you that the node is actually displacing up when you're forcing it down. And so that of course is not going to be physically consistent. And so, it's a little bit involved. And so there's quite a few steps to this, but once you kind of do it a few times, you kind of get used to computing the angles like this. And this just makes sure that your angles are just always consistent in that case. Yeah. Okay. All right, and so now that we know the angle and we know what cosine and sine are, we can go ahead and run through the element stiffness matrices. Okay, and so the element stiffness matrix for A is going to be F1x, F1y, F2x, F2y. Okay, is equal to 2.5 times 10 to the 5th pound per inch. Okay. And I'm just in the interest of time, it's already 8 o'clock. And so I'm going to go ahead and just fill in the values for this. So it's going to be 3/4 minus √3/4 minus 3/4 √3/4. Okay, this is going to be 1/4 √3/4 minus 1/4 3/4 minus √3/4 and then 1/4. Okay. And of course, this is a metric, so we have minus √3/4 minus 3/4 √3/4. Okay. √3/4 minus 1/4 and then minus √3/4. Okay. And of course, that's multiplied by u1x, u1y, u2x, u2y. Okay. So go ahead and write that in. u1x, u1y, u2x, u2y. Okay. All right. That's element A. Okay. So now let's go ahead and do element B. Okay. So element B here, we have EA over L. Okay. And so the Young's modulus for this element is the same as before, but the length is half. And so what we get is 5 times 10 to the 5th pound per inch. Okay. Our theta here, let's go ahead and look at the diagram. And we'll do the same thing we did before. And so we're going to go to node 1. I'm going to write in my coordinate axes. Okay, so we have y and x. Okay. Because 1 here is the lower numbered node. And so in this case, we're going to rotate all the way over like this. Okay. And so the angle for element B is 180. Okay. And so cosine of 180 is -1. Sine of 180 is 0. Okay. All right, so let's go ahead and fill this in. And so the element stiffness matrix for this is F1x, F1y, y, F3x, F3y is equal to 5 times 10 to the 5th pound per inch. Okay. Multiplied by 1, 0, minus 1, 0. 0, 0, 0, 0, minus 1, 0, 0, 0, and then 0, 0, 0, 0. Okay. And then we have u1x, u1y, u3x, u3y. Okay. All right. Any questions on this? Okay. All right. And so those are the element stiffness matrices. And of course, the next step is to assemble. Okay. And so assembly here is just going to be a, it's just going to be a 6 by 6. And so it's going to be a little bit easier than the last one. So we have F1x, F1y, F2x, F2y, F3x, F3y. Okay. Is equal to u1x, u1y, u2x, u2y, u3x, u3y. Okay. Oh yeah, it's 1. Thank you. I missed that. Yeah. Thanks for that. Yes, of course. Question. So the angle of element B will change as there is roller support. Will that in any way affect the solution? We'll see. And so we'll you'll see from the result. Okay. All right. And so let's go ahead and start filling these in. And so we have a 10 to the 5th on the outside. Okay. And so element A here, element A is going to be nodes 1 and 2. So that's going to be these entries right here. Okay. And then element B, this is going to be nodes 1 and 3. Okay. So that's going to be this block, this block, this block. I don't know why I'm drawing dotted lines, just draw solid ones. Okay. All right, and so I'm going to go ahead and just fill in the entries here. Okay. Knowing that node 2 is fixed, and so I'm going to go ahead and avoid that one. Okay. Okay. And node 3 has a roller. Node 3 has a roller that prevents displacements in the x direction, right? Because our roller here is vertical, right? And so that means u3x is going to be 0, but u3y is going to be free. Okay. Okay. And so with that in mind, the second row in the matrix, oh, I kind of drew this kind of scuffed, huh? Okay, so the second row is going to be 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0. Okay. And then the second to last row, node 3, where u3x is equal to 0, then that's going to be a 0, 0, 0, 0, 1, 0. Okay. Right. And so, you know, for this problem here, I'm taking a shortcut where I'm kind of prematurely applying our boundary conditions just so we don't have to worry about it later. Okay. And then for everything else, I'm going to go ahead and apply our combining element stiffness matrices. Okay. So this one's a little bit annoying because we have 30 degrees here, so we have lots of 3s and 4s kind of floating around. And so if you compute those and you multiply by the 2.5 out in front, then we get the following values. So we get for this one right here, we get 6.85, 6.875. Okay. We go minus 1.08, and we go minus 1.08, and 0.625. Okay. So that's the result of combining both together. Okay. And then for these entries right here, we have a minus 1.875. For this one right here, we have a 1.08. This one right here, we have a 1.08. This one right here, we have a minus 0.625. Okay. And then for the top right here, we have a minus 5, 0, 0, 0. Okay. And then for the final row, we have 0, 0, 0, 0, 0, 0. Okay. Okay. Oh, and we have the entries on the right. And so we said that F2x, F2y, F3x, they're all going to be zeros. Okay. Okay. And in terms of our loads, you know, our load is a load of 25,000 pounds applied vertically downward on node 1. Okay. And so that means that our F1y here is going to be a minus 25,000. And our F1x here is just going to be 0 because we don't have any load there. All right. A little bit rushed, I know. I apologize, but you know, but this is kind of the same, you know, but this is the same process that we've gone through, and so, you know, I've just kind of accelerated a few of the steps. But if you want to see, you know, a lot of the full details of this example are given in the notes. Any questions on how we got to this point here? Okay. All right. And so now we're at a point, and let me go ahead and clear this because we don't have any vertical force on node 3 either. Okay, so this is going to be 0. Okay. All right, and so at this point, you know, we've taken our element stiffness matrices, we've assembled them into the global stiffness system, we've applied our loads and constraints, right? And so we should be able to solve, right? And so if we plop this into MATLAB, we should be able to solve, right? You should, but if you try popping this into MATLAB, MATLAB is going to complain. MATLAB is going to complain that you're going to have a singular matrix or something. Okay. Okay. All right. So why is that? So the reason MATLAB is complaining is look at the matrix that we have here. Okay. Look at the last row in the matrix and the last column in the matrix. Okay. Right. Every entry in this last row and every entry in this last column are all zeros. Okay? And so this can't happen. And so if you have a situation like this where you have all zeros in a row and all zeros in a column, that means your system is under constraint. Okay? Under constraint basically means that there's not enough constraints there to constrain all the motion, right? Because an assumption that we've been making this entire time is that all the displacements that we're getting, none of them have anything to do with rigid body motion. And so they're all just kind of small deformations of the elements themselves, okay? When you have a global stiffness system which has all zeros in a column and all zeros in the row, that means that node's under constraint. So let's go back to node 3, right? And so what that tells us is that node 3 here, the y component is under constraint, okay? And so that means that, you know, and that makes sense, you know, because if we look back at a node 3 here in our system, you can see here that we're letting it kind of roam free, okay? What this means is that, you know, when we have this system here and we start pulling down on this node with the force of 25,000, that means that this node right here is not going to be constrained, and it's just going to start moving, you know, freely. And so there's nothing there that's going to really constrict its motion. Okay. And so what's going to happen in a situation like this, you know, if you want to kind of play it out, right? And so it's going to start something like this, and then just the displacements are going to get extreme. And so as soon as you start pulling down, or even before that, actually, even just through gravity, you know, this bar is just going to start rotating like that. And it's going to keep rotating until it reaches kind of its physical limit. And so the displacements are kind of too large for it to handle. Okay? And so the only way to solve this problem, when you get a situation with all zeros in a row in the column, is to artificially increase the amounts of constraints. And so the way that you can do it, you can kind of transform this roller constraint into a fixed constraint. And so if you add a 1 right there, then that transforms it. Yeah.
Don't you have that every time you have a roller?
So for these problems with truss bars, it is very common because remember the truss bars are only allowed to just expand and contract. And so it's not really until we get to frames where we're going to allow the elements to also rotate, then we're actually going to get something reasonable. But for these truss bars, most times if you do just rollers with trusses and springs, then this is going to happen pretty commonly. Yeah.
Is this like the pen and paper equivalent of Ansys telling you to turn large deformations on? Well, Ansys
kind of.
will give you a solution, but it'll be inaccurate.
Yeah, kind of.
So
You can
like
think of it
us
like that.
having this one is kind of just like, okay, we turned our large deformation.
This is, you'd actually turn it off in this case. And so you'd add basically additional constraints to make it so that you don't have any large deformations. Yeah. All right, question from Sam. So wouldn't the 5 feet be the constraint? It is. And so eventually this truss bar is going to rotate to a point where it reaches a stable position where it is stable with 5 foot. And so I think for this one, it might be something like this, right? And so when when that truss bar kind of reaches that angle, then it's going to be stable, right? And then you can actually compute something. But what this is telling us is that in this configuration, where this truss bar here is horizontal with this roller, it's under constrained and it can't hold this for that much longer if that's a roller. Yeah. Yeah. So it's saying that this configuration is unstable. That's basically what it's saying. Yeah. Okay. And of course, the top bar is going to rotate as well. And so it's not just the bottom one's rotating by itself, but the top one's also going to rotate kind of this way as well as this one rotates that way. Yeah. Yeah. And so if you want to, basically, this is telling you if you want to maintain this configuration, you have to constrain that node some more in order to maintain it. All right. And so, if you come across a situation like this in your homeworks, most time it's going to be due to a roller, then you can artificially, constrain it even more by adding that fixed constraint. Okay. All right. Any final questions on this before we wrap it up for today? Okay. All right. And so that's all we have time for today. And so it's only 2 examples, but these problems are really time consuming, and so it takes a lot of time. And so on Thursday, on Wednesday, I have one last thing to talk about here, which has to do with symmetry, which is a really interesting topic in finite elements. And then after that, we're going to start talking about beams, which is the next kind of structural element that we'll talk about. Okay. All right. So thank you everyone for tuning in today. I know I went over by a few minutes, and so thank you guys for your patience. Oh, question.
Do you have class next Monday?
Yeah. So next Monday is a holiday, so there's no class next Monday. But I will be holding office hours on Monday, and so if you want to chat about anything, I will be holding my regular office hours. But I won't be here. I'll be home because I don't want to drive here, just stay here for an hour and then go home. And so if you want to talk, I'll be on Zoom. Just join the Zoom room. Yeah. Okay. So thank you everyone for tuning in. Hope you guys enjoy the rest of your evening. If you have plans for Valentine's Day at the very end, hope you guys enjoy those. Hope you guys have a good time. And so I'll see you on Wednesday. Thanks, guys. Have a good night. See you Wednesday.
I just wanted to double check with you that I started this one correctly.
Sure.
So I just set up all these stiffness matrices here,
Uh-huh.
right? So for the spring here, and then for the bar here,
Yep,
and then again here,
Yep.
and then I'll just combine all this.
Yep. So, and so, you know, when you combine it, it make kind of a nice pattern. So, and so it would be, you know, because they're all sequenced and so they're all in series.
Uh-huh.
And so for something like this, it would look, you know. And so I didn't draw this, you know, it would look like that basically. Yeah. Yeah. But they're all going to overlap on their corners. So like this one's going to overlap with this one because you can see they're both F2 right here.
Mhm.
And then this one's going to overlap with this one. Yeah, both F3.
Okay.
And then this one's going to
So
overlap.
it's just the same thing, you're just using different stiffness.
Exactly,
versions.
right.
Okay.
Yeah. And so for those ones, you're going to have like a stiffness or a spring constant plus like AE over L,
Uh-huh.
and that's fine. And so, you know, they all have the same units, so you can have them together. Just
Yeah, initially they just look scary, but I guess it's just the setup. Like this looks wild, but
that was a new one that I made up just for this.
all right, well, try that and I'll probably be asking you questions.
Okay. Victor, Dustin, did you guys have any final questions? Or there's a Victor in here, that's why. Okay, all right, so I'm gonna go ahead and close the room. So I'll see you Wednesday.